This is the Earth Science Classroom, and welcome back. This is the Earth's Interior Unit, looking at convection currents. This is actually video 2, which follows along from video 1 on convection, where brief summary of video 1, basically we discussed what convection is. We discussed who were the pioneers on figuring out basic convection from Newton to Rumford to DeLong and Petit. So in the 18th century and early 19th century, these scientists pioneered the idea of thermal and radiant energy movement through different mediums. Then we looked at the basics of convection, which was thermal energy moving from a hot area to a cold area. Thermal energy wants to even up. It wants to be equal. It wants to be balanced. It also works across the whole planet, as it does in small examples. And we discussed why, let's say in the troposphere, why hot air actually rises. I went into the physics of thermodynamics and the first law and energy and the air parcel. So now we're going to get onto the Earth's interior. We're going to look at the layers in particular that respond or reflect convection currents. So if we're looking at our Earth's layers, let's look at the upper mantle in more detail. So I have my Earth's surface. I'm just going to draw me an Earth's surface. There we go. So we live on or upon the Earth's crust, the very thin external layer of the Earth that we exist on. And then so it's very thin, okay? And then we get on to the next layer, which is the lithosphere. And lithos meaning the rock. Now, to be detailed, the crust is a part of the upper lithosphere. And this extends down to roughly 100 kilometers below the surface. That may extend deeper based on a term called isostasy and flotation, buoyancy, but generally it's 100 kilometers. Then you have a thing called the MOHO, which is a shortened version of the Mohovich discontinuity, which is based on a European scientist in 1909 who used seismic waves to decipher or show the difference in velocities of those seismic waves as they traveled through the Earth, and they were created by an earthquake. So what he did was he measured the velocity or speed from the earthquake to seismic recorders or stations on the surface, and he would record at different distances these waves, and he figured out that the deeper the wave, the faster it went. There was a kind of a consistent speed at which waves go through the crust and lithosphere. However, when the wave, for example, goes down below lithosphere, it's going to go from an average of 6 kilometers a second to 8 kilometers per second, and it's going to travel faster. So there was an increase in velocity below the lithosphere. This kind of allowed him to differentiate the layers using seismic waves. And that brings us to our next layer. Next layer is a lot thicker. All right, so it extends from roughly 100 kilometers, as I stated before, down to about 660 kilometers, or there or thereabouts. And we call this the asthenosphere. Now, in ancient Greek, this works out as the asthenos means not strong. So astheno means strength, and we get an A in front of it. It means to not have strength. So we call it the weak sphere. of the rock. We're still in the upper mantle, and this 660-kilometer boundary is called the upper mantle and lower mantle separation. So from here down, we have the lower mantle. So we're kind of like we're basically going between the chemical layers and the physical layers of the Earth. Chemical is basically the rock mineral composition, and the physical is the temperature and density and the state of matter. So there's differences in the layers. So now we're in the lower mantle, and we call this the meso or mesosphere. Meso is a word that means middle. It's also the similar word, same word that we find in a layer of the atmosphere above the surface of the Earth, which is kind of confusing, but you know, is what it is. So we have this area right here, the asthenosphere, being the weak sphere. Now, why is it the weak sphere? There is an area found by seismic waves, which is called the LVZ, low velocity zone. This is where the seismic waves were recorded to slow down or reduce their velocity in this area between 150 to 250 kilometers. So it's within this asthenospheric layer. So it's about here. And this is where we presume, we scientifically estimate that this is where a lot of the magma is created or resides within this layer. The above crust lithosphere is solid and rigid. Rigid meaning it doesn't move. It is solid and it's a solid structure, but it doesn't move. The asthenosphere is solid, and it has a higher density than that of its above counterpart, the crust of the sphere. So it's got a density of 3.3 down to roughly 5.7 grams per centimeter cubed. Now, the rule of thumb is as you go down deeper, you increase both the density and you increase the temperature. So there's a kind of fight off between those two properties, density and the temperature. So this area of magma is formed through an increase in temperature or the geothermal gradient compared to the density, so, or the pressure as well. Because there's too much pressure and too high density, then you really can't, no matter how hot it gets, you really can't melt that material, because in order for a material to melt, it needs space in order to melt into, because when you change or have a phase change from a solid to a liquid, you generally increase the volume to make it into a liquid, because the atoms are moving over a greater distance. It's enlarging its volume based on the energy and the amount of bonds and the structure of that material. A solid is usually going to be a three-dimensional shape or lattice or matrix where it's rigid and it's a set distance between the atoms, whereas liquid is obviously, it can change the shape, it can change and be malleable. So if there's too much pressure applied to that three-dimensional solid, then no matter how hot it gets, it cannot expand and turn or phase change into a liquid. The only thing that changes on Earth, really, that's the most obvious one, is And that changes its density is water. So water actually gets more dense as a liquid compared to a solid. That's why water is very unique on this planet in terms of its chemistry and physics. So in this region, the LVC region of the asthenosphere, or even in the whole asthenosphere, you get a temperature is greater than pressure. So what you get is the melting of parent rock or source rock or country rock, and you get the creation of melt. We know it as magma, which is basically liquid minerals, and there will be some gases in there as well, dissolved gases. So this magma, okay, is a fluid, okay, and it's partially, so this whole area, this whole thing is partially solid, and there's a small amount that is magma. And we get this difference in temperature. So as I said before, convection, it's all about a difference in temperature, and it's hot down here, so the temperature is going to be around 2,700 degrees Celsius, and up towards the lower lithosphere, deeper part, okay, about 100 kilometers, it's going to be about 1,200 degrees Celsius. So there is a temperature gradient, a difference between 2,700 Celsius and 1,200. So the hot material is going to rise up, it's going to cool down, and because it's a rigid, solid lithospheric plate above it, you can't go through it very often, and it's going to recycle back down. And again, this mesosphere is solid and mostly pyrrhotite. Okay, a lot higher density, so it can't go down. So it stays in the asthenosphere as a circulating convection current of moving material from hot area towards the mesosphere, up to the colder area, up to the moho and lithosphere. So you have this convection current, CC right here, that is consistently moving in this system because the Earth's interior heat is consistent. Even though it is cooling down slowly, it is still consistent over our knowledge of time. So convection current, so you have this simplified version of the crust, lithosphere, asthenosphere, and mesosphere, or CLAM, as an abbreviation, a short acronym. You have these convection currents that are moving from hot to cold, and it is pretty much the mechanism that Holmes in 1919 suggested was the reason behind Wegener's 1912 funnel drift theory on how the plates are physically drifting across the Earth's surface from Pangaea to their current location we know today. So, hope this helps clarify and break down the layers and what is important to know, what isn't. So, hope this helps. Please subscribe and leave a comment, and look forward to having you in the next video.